Okay, welcome back to our lecture on a practical guide to quantitative finance interviews. This is going to be our 11th lecture, and today we are going to talking about the 10 must-do probability questions. All these 10 questions are the most classic ones in probability theory field. Okay, and so let's start. The first one is called Monty problem. But it got another famous name called like the three-door problem. Okay, 三门问题. So basically, the Monty problem is a probability puzzle based on an old American show. Let's make it here. So the problem is named after the show's host, Monty Hall. Suppose you are on the show now, and you are given the choice of three doors. Behind one door is a car, and behind the other two goats, you don't know ahead of time what is being each of the doors. So you pick up one of the doors and announce it. As soon as you pick the door, Monty opens one of the other two doors that he knows has a goat behind it. Then he gives you the option to either keep your original choice or switch to the third door. So should you switch, and what's the probability of winning a car if you switch? There is a joke about this question is that if you could answer this question correctly in the first time, and then you have a gift for the quant industry. Okay, but a pity that I answered this question wrong during the super day of HSBC. Okay, sad story. So I think let's first propose this graph here. Suppose we choose, let's use, suppose we choose door one, okay. We pick door one at first. Then all the situations are listed here. There is 1/3 probability for the car to be at door one, door two, and door three. And if it is at door one, then the host can either open two or three because ghost is behind the door two and three. And if you see that, you can see actually the state and switch is similarly the same. So like this is where we lost, right? And this is where we win if we switch, loss if switch. And you can see actually if we switch, the probability of win conditional on switch is going to be 2 multiplied by 1/3, which is 2/3, right? Which is larger than our original probability of winning, which is 1/3. So, but the thing is that if you are in the middle of the interview, it's hard for you to list all these kind of probabilities, and it will look silly, right? Is there any simple and elegant way to solve this question? There is. You need to look at the problem from a different perspective. So let's see, originally speaking, if we can't switch, then win means what? Means we pick the car door, right? And the car door, there is only one car behind three doors. So it must be 1/3, right? But if we switch, then you can see if we pick the door one, right? And this is a goat. Door two, this is another goat. And this is a door that the host picked. And then door three must be the car, which means if we switch from goat, if we choose to switch, then our winning strategy is that we will win if pick the goat at first. This is pick the car door at first, right? And we know that there are two goats within three doors, then it's 2/3, which means this gives us a higher probability of winning. Because this time our winning condition becomes picking goat at the first at the very beginning of this game, right? So I think this is the easiest way to think of this question. And now let's come to the second one, which is called amoeba population. There is an amoeba in the pond. What is amoeba? Is it 阿米巴原虫, okay? Which is a kind of like some kind of bio insects. I don't know. I'm not a chemist. So after every minute, the amoeba may die, stay the same, split into 2 or split into 3 with equal probability. And all its offsprings, if it has any, will behave the same and independent of other amoebas. So what is the probability of amoeba population will die out? Which means there will be 0 amoeba left at some moment, right? So now let's define this event. So this event E, let's just call it, equal to amoeba dies out. And then we use the philosophy that we start with the simple case. At the very beginning, there is only 1 amoeba, right? And it can die, stay the same, split the first case, the second case, the third case, and the fourth case with equal probability. Okay. So now probability E will be equal to what? Probability E, conditional case 1, multiplied by the probability of case 1, right? And plus probability E of case 2, multiplied by the probability of case 2 plus PE. And we all know that these probability, because they will have with equal probability, so they are all 1/4. And let's go back, and this is 0 multiplied by 1/4 plus probability E conditional on case 4 happen, multiplied by 1/4, right? And now we just need to discuss the result of these 4 probabilities, and then we can get to the answer, right? So conditional on it die, then the population die out is equal to 1, right? Because we at the very beginning only have 1 amoeba, so if it dies, then the whole population dies out. And for the second case, if it remains the same, then this is going to be just probability E, right? We can replace it. And if we got to split into 2, which means there are 2 amoebas, and each of them will behave independent of other amoebas. So we need each of them to die out, and there are 2, so we just need to take the square. And if they split into 3, then it's just probability E and 2 the cubist. So we can see what, if we denote PE as X, we can have X equal to 1/4 plus 1/4X plus 1/4X squared plus 1/4X cubist. And if we're trying to solve this question, we can get this X is equal to square root 2 minus 1, which is around 0.414, right? So by the way, you need to remember these 2 numbers. Square root 2 is 1.414. And what about square root of 3? It's almost 1.76, okay? And now let's come to the third question, candies in the jar. So we need to introduce one classic philosophy here. Let's first read the question. So you are taking out candies 1 by 1 from a jar that has 10 red candies, 20 blue candies, and 30 green candies in it. And what is the probability that there are at least 1 blue candy and 1 green candy left in the jar while you have taken out all the red candies? So it seems a complex question and you don't know how to frame this one, right? So I want to introduce this principle of tail of, let's say, last one. Usually for this kind of question, the only thing we need to concern is the last one. So for this question, we can rephrase it into this. Let's suppose we take out candies 1 by 1, right? So we got like the first peak, the second peak, all the way to the 60th peak, right? And we can write three things, which is tail of red equal to the number Pn, which is the last red candy was picked when the last one. Which means if for the, let's say the 20th candies, it's going to be the last red candy, then TI is going to be 20. And the same, we are going to have T green and T blue, right? So we are, then this question is asking the probability that at least one blue candy and one green candy left when we have taken out all the red candies, which means the tail red must be smaller than tail green, tail blue, and since these two are mutually exclusive, we can take the sum, T blue or T green, right? So we just need to calculate these two things. And then let's break down these two probabilities. So let me try to insert a page here. This probability TR smaller than TG smaller than TB is going to be probability TR smaller than TG and multiply by the probability that blue is the last candy color, right? And since any candy can be the last one to be picked with equal probability, and there are 20 blue candies out of 6, so this probability is just a 20 over 60, right? And now for this one, within the previous candies, we want the green to be the last one, right? So how possible is likely that the last candy is going to be a green one? It is going to be, since there are 10 red candies and 30 green candies. So out of the 40 candies, there are 30, right? Because we have considered the blue cases, then any other blue candies except from the last one, we do not think about it. So we only need to think about the green and the red candies beforehand. And within them, we want the last one to be green, right? And out of the 40 candies of red and green, there are 30 green candies. So we just need to multiply these two together. Then how about another probability, this part? This TR smaller than T blue, smaller than T green, right? Again, this could be break by TR smaller than TB multiplied by the probability that green is the last color, right? Then out of the 60 candies, which could all be the last one with equal probabilities, there are 30 is green. And there are 30 candies left. Among them, how many of them are blue? 20 are blue, right? So then now we have the total probability equal to 30 over 40 multiplied by 20 over 60 plus 20 over 30 multiplied by 30 over 60. These two cancels out, and this is equal to 1 over 3. These two cancels out, these two cancel out, and this is 1 over 4. So in total, this is going to be 7 over 12, and we solve this question. So in this question, I introduced this new principle called tail. Actually, this is quite important philosophy or idea that could help you to think many questions, especially for coding related questions. Sometimes when the judgment is need to be made only based on the last one, you can use this. You could rephrasing the question with the last one of every type of the things that is listed in the question, okay? So now let's come to the next question, which is coin toss game. This one is also quite classic. So two players, A and B, alternatively toss a fair coin. A tosses a coin first, then B tosses a coin, then A, then B. And until the sequence of heads or tails happens like a head followed by a tail. And the game will end, and the person who tosses the tail wins. So what is the probability that A wins the game? So now let's first define the event again. Equal to A wins the game. For this question, I hope you still remember another principle we introduced the last time, the principle of symmetry, and we are going to use that. So probability E is going to be probability E conditional on first is head, okay? Since it is a fair coin, then the probability of head is 1. So this is just 1/2, right? And another thing is just probability event conditional on first is tail. And so this again is going to be probability tail, which is also 1/2. Then we just need to solve these two things. So conditional on the first is the head, then the thing is that if the first, I have already tossed the hand, then there will be 1/2 probability for B to toss the tail, then B wins. So the chance of my win is going to be 0, right? And there will be another probability if B also tosses a 1/2, then it is going to be 1 minus probability E conditional on first is head. Because if B also tosses the head, then A suddenly becomes in B's situation, right? So they are replaceable again by the principle of symmetry. And on the other hand, if the first is tail, then the probability is going to be probability B wins, right? Because if the first one is tail, it's basically the same as we start from a very new game. So it is going to be just a 1 minus probability E. And we know this part is going to equal to this part. So probability E first hand is going to, so X is going to be 1/2, 1 minus X. So we can have X equal to 1/3. Then the original theory, if we define this as Y, then Y is going to be what? 1/2 multiplied by 1/3, which is solved here. And plus this we know is 1 minus Y multiplied by 1/2. And if you solve this one, you can get that. So 3/2Y is going to be 7/6, and this is going to be Y will equal to 4/9. Oh yeah, sorry. So this is 1/2 here plus 1/6, so it is 2/3. Yeah. So the probability that A wins the game is 4/9. You can see A actually has a less chance to win. You could think it why, because for the second player, at the very beginning, he has already got some chance to win at the first toss, but that's not the case for A, right? So because it must to have two, at least there will be 2 tossing to have a winner, at least. But there is no chance for A to win at its first toss. But there is a chance for B to win at B's first toss because he is the second player. So actually the later player got the advantage. So if you are the one who is playing this game, I could ask you that, should you want to be A or B? And you should choose to be B, okay? And now let's come to the Russian roulette series. That's quite a traditional game, okay? So you have a single bullet is put into a 6-chamber revolver, and the barrel is randomly spawned so that every chamber is equally likely to be under the hammer. if it is on the hammer, then it means the bullet is going to be shoot. Okay, and two players take turns to pull the trigger, with the gun unfortunately pointed at one's own head without further spinning until the gun guns off and the person who got killed loses. So basically, you got killed, you lose. Okay. If you, one of the players, can choose to go first or second, how should I choose? And what is my probability of loss? So since each chamber is equally likely to be under the hammer, so the first player has a 1/6 chance to be hit, right? Probability got hit at the first time is going to be 1/6. And then once it has been spurned, once it has been spurned in the chamber, okay, the barrel is spurned, then the position of the bullet is already fixed, which means we have, let's draw a picture here. So we have one, let's make it bigger. 1, 2, 3, 4, 5, 6, right? Once the barrel is randomly spurned, the bullet has been fixed its position. And the first player is only going to be killed at 1/3 or the 5th position. And the second player is only going to be killed if the bullet is at the 2nd, 4th, or the 6th position. And since the bullet is randomly positioned among these 6, so basically the probability of loss is just 1/2, and choose to go first or second doesn't matter, okay? But now let's come to some variant of this question. Let's change the rule slightly. We will spin the barrel again after this trigger pulls. So now will I choose to be the first or the second player? And what's my probability of loss? Again, so we just define the event like A will get killed. Okay, so which is the first player? A is the first player. Okay, then this probability E is going to be 1. There is 1/6 probability that the first at the first trigger, A has already got killed, and that's 1/6, right? The bullet is at the first position, so this is multiplied by 1. The probability get killed, and plus there is 5/6 position to start a new game, because each time we will spin the barrel again. So which means basically the game becomes new. The precision of the bullet is randomized again. So this is just going to be similar as 1 minus probability E, because for the second round, it's going to be the turn of the second player, which is B. And if B gets killed, we win, right? The first player win. And to solve this one, we could get the probability A win equal to 5/11, which is smaller than 1/2. So we should choose to be the second one. Again, just quite similar like the coin toss game. Actually, the second player in this situation takes the advantage by it actually has a less chance to lose, because at least he can hold 1 round longer. He has no chance to be killed in the first round, because the first player could just get killed at the very beginning, while B has not even touched the gun. Okay. And then let's come to another variant. If instead of 1 bullet, 2 bullets are randomly put in a chamber, and your opponent played the first and he was alive until the first trigger pull, and you are given the position whether to spin the barrel or not. Should I spin the barrel? So after the first one has pulled the trigger, we know this one is empty, right? Then we know this one is empty. So if I did not put, and there are 2 bullets, okay? then if I did not spring, there is what? There is 2/5 probability for me to get killed, right? If not spring, And if I spin it, then the game become randomized again, right? So there will be 2/6 probability to get killed, which is 1/3 less than 2/5. So I should not. Now let's come to our last variant. What if the two bullies are randomly put into consecutive positions? And again, your opponent badly survived his first round. Should we spring the bill? So by put two bullies into consecutive positions, it means as long as we already know the first position is empty, then we could think 2, 3 as one position, 3, 4 as one position, 5, 4, 4, 5 as one position, and 5, 6 as another position. So there are only 4 positions left, and one of them is going to contain 2 bullies, right? So my chance of got killed, if not spin, is now 1/4. But if I spin it, then again, it is going to be 2/6, which is 1/3. So should I spin it? You still should not spin it. Because if you don't spin it, you got a less chance to be killed, okay? Now let's come to the next one. The next one is aces. Again, our good friend cards is coming back. We have the 52 cards, and they are randomly distributed to 4 players, with each player getting 30 cards. And what is the probability that each of them will have an ace? So ace is just the A, okay? Ace is just the A. And there is the saying like called ace in the hole. This is the saying in English, which means in Chinese is 最终王牌, which you could also call silver bullet. It's like your last chance of winning, or it's your your best play, your best skill set. Okay, so and what is the probability of each of them have an ace? This is actually a good question, combining conditional probability with permutation. So let's first find all the permutations we could have if we are just randomly distributed through 4 players. So we know there are in total 52 cards. So the permutation is 52. And we are going to distribute it into 4 groups. Each has 13. So this is going to be the number on the denominator, okay? But how about on the numerator? On numerator is that the probability each of them will have an ace. So which means the 4 ace is going to be distributed in the 4 position. And how many permutations are there? There are 4 factorial, right? And then how many cards left? There are 52 minus 4, which is 48 factorial. And they are going to distribute it then into 12, 12, 12, 12. Because each one of them has already got an ace. So each of them need to get 12 more cards to form a 30 card group set. And this is actually easy to be solved. So we have 4, and this is 48 factorial. And we know that 13 factorial over 12 factorial is equal to 13, right? So if we multiply that, then we can have and we can cancel this out. This is 52 multiplied by 51 multiplied by 50 multiplied by 49, right? And if we put this part multiplied out again, if we multiply this part both on the denominator and numerator, and then we are going to have 13 to the power of 4. And now if we try to solve that, we could have this thing, which is 1 multiplied by 51 over 39 multiplied by 26 over 50 multiplied by 13 over 49. Okay, and you just need to calculate this value. Okay, now next question is super famous. Gambler's ruin. So it got a lot of variant of this question. If the interviewer wants to make it hard, it can be super hard. But this time we're only going to introduce the fundamental set. So the gambler's ruin problem's classic framework is that there is only one gambler. And it starts with the initial fortune of $I, and on each successive game, the gambler wins $1 with probability P, or lose 1 with probability Q. Okay, and which is just 1 minus P. So he will stop if he either accumulated N dollars or lose all his money. And what's the probability that he will end up with N dollars? So let's say that the probability of winning with let's just use smaller n, okay, with N dollars in hand at the beginning. We denote this as Pn. And what are we going to find? This n must be smaller than n and smaller than 0. Okay. We can use the equal here. So then Pn is going to be what? Pn is going to be Q multiplied by Pn plus 1, right? And plus P Pn minus 1. Oh no, sorry. Sorry, I'm wrong. This should be Pn minus 1, and this should be Pn plus 1. This means that there is a Q probability that he is going to have only N minus 1 fortune. And then the probability becomes Pn minus 1. And there is also P probability that he could have $1 more. So the situation becomes, it starts with the N plus $1. It's actually already have the idea thinking of Markov chain, while your future position is only conditional on your current position, but has no relation with all the historical movements, okay? And let's reframe this a little bit. So if you divide it, if you have some numerical sequence knowledge, you know, one thing to deal with this thing is that we just divide each part with Q. So we can have Pn plus 1 minus Pn is going to be what? It's going to be Q over P, Pn minus 1. Well, it's actually quite easy to check this thing. You can check it out because P plus Q equal to 1, and you just need to put a P plus Q here, and everything becomes quite easy to be seen, right? And now we can further denote this Pn plus 1 minus Pn as something, let's call it An plus 1, okay? Then we have An plus 1 equal to Q over P. Let's denote this as a C, okay? Let's denote it as C. Okay, let me rewrite it. So let's have Q over P equal to C, then this is going to be CAN. And now it's just a geometric sequence. We can have that Pn is going to be Cn's power of P1, right? And we know that if we want to, oh, sorry, this is A, okay. This is A. An is going to be A1. And we know that if we want to find Pn equal to what? Pn minus 1 plus Pn minus 1 minus Pn minus 2, all the way to plus 2 P2 minus P1 plus P1 minus P0. And so Pn is actually equal to what? Equal to 1 plus C squared all the way to C n minus 1, right? And this is going to have Pn is going to be 1. Because if we start with $n, then our probability of winning is just 1. But it will also equal to this 1 plus C plus all the way to Cn minus 1 and multiplied by 1 P1, okay? And this is going to be 1 minus C, 1 minus Cn multiplied by P1. But only if this C not equal to 1, okay? If C equal to 1, then it is just NP1. Why can we not cancel out this P1 here? Because at the last here, we don't know what is PZ. We don't know what is P1, okay? We don't know what is P1. So we know P0 equal to 0. So we need to remain one P1 here, and this needs to be denoted as CP1, right? Because P1 equal to A1. That's the thing, okay? So we need to still have a P1 here. And this is our final solution. So by getting that, we can have 1 equal to Pn equal to 1 minus C to the power of n over 1 minus C multiplied by P1. So P1 is equal to 1 over C, 1 minus Cn, right? If C does not equal to 1 and P1 all equal to 1 over n, if C equal to 1. Because if C is 1, then it's just the sum of NPs, right? This is 1, this is 1, this is 1. And so there are in total n of that, so it's NP1. And now Pi is just what? Pi is just if C equal to 1, then it's just I over n. For I smaller than 0, smaller than n. And if C does not equal to 0, no, does not equal to 1, then we simply just need to multiply it with C this I here. 1 minus Cn. Why is that the case? Because from this solution, we can also get is what? We can also get Pi equal to 1 minus Ci over 1 minus C multiplied by P1. And we just replace this P1 with this part. And combine together, we can cancel these two out. So it becomes this format. Okay? So it's just becomes inverse of a geometric sequence typical sums formula. Okay? And now let's come to the next question, which is basketball score. The basketball score is that you have a basketball player and they are taking 100 free throws. You know, Kobe Bryant used to throw like over 3,000 balls at 3,000 throws a day. I don't know. So she scores, oh, it's a girl. Okay. She scores 1 point if the ball passes through the hoop and 0 point if she misses. And she has scored on her first throw and missed on her second. For each of the throw, the probability of her scoring is the fraction of throw he has made so far. So for example, if he has scored 23 points after the 40th throw, the probability that she will score in the 41st throw is 23 over 40. And after 100 throw, what is the probability that she scores exactly 50 baskets? So it seems quite complex question, and you don't know what's the pattern of that. To find the pattern again, we start from simple case. Okay. So we already know that he made the first one. The first one is okay, and the second one is has missed. So for the third player, so probability scores of 3 baskets is just 1/2, right? It has 1/2 of scoring at the third throw. And in total, if we denote it at this is going to be probability 3/2. What does this mean? So Pij means that at ith throw, let's say after, okay, let's say after. After ith throw, J scores have been got. Okay. And now let's see probability of, let's say 4/1. Probability 4/1 is going to be, so we need to miss both. So it is 1/2. On the third play, we need to have a P3/1 first. And then if we already have a P3/1, this is P3/1, okay? We need to keep missing it. So in this condition, the probability of winning is just 1/3, right? Of the fraction of this. So yeah, so the probability he is going to through is 1/3. And so this is going to be 1 minus 1/3, which is going to be 1/3. How about probability 4/2? Probability 4/2 equals to probability 3/1 multiplied by probability win at fourth plus probability 3/2 multiplied by probability miss at fourth, right? And this is going to be, this is 1/2, and again, this is also 1/2. And win at the fourth, as we see, if it is 3/1, then it is 1/3, which this part gives us 1/6. And if we miss at the fourth, when we already got 2, then it is going to be 1 minus 2/3, which is also 1/6. So in total, this is going to be 1/3 again. So, and you are going to find that P43 is also 1/3. And so basically, Pn, no matter what this J is, okay, no matter this J is, it's going to be 1/n by induction. And you could prove that by the mathematical inductions, n-1, sorry. And now we are asking what's the probability that C scores exactly 50 baskets. Then probability 150 is just going to be what? 1/99. Okay, you see, for this kind of question, do not panic. You just need to first start from the very simple cases, and equals to 1, equals to 2, and equals to 3 and 4, trying to find a pattern, and then prove the pattern using mathematical induction, which is neglectful during the interview. As long as you can find the final answers and show your logic to your interviewers, it's fine. And yeah, basically, I think it's the fastest way to help you get that during an interview. So now let's go to our last question, cars on road. If the probability of observing at least one car on a highway during any 20-minute time interval is this number, 609/625. Then what is the probability of observing at least one car during any 5 minutes interval? So assume that the probability of seeing a car at any moment is uniform for the entire 20 minutes. So the probability of seeing at least one is what? It's just 1 minus probability seeing no car, right? Seeing no car during 20. Oh, it is during any 5 minutes. Seeing no car during all 5 intervals, okay? And this is going to be y minus p 4 probability. So this is good. So let's just denote this one as P. Okay, let's denote this one as P. See no car during all 5 minutes. Oh no, let's just denote this one as P. Then probability seeing no car during all 5 minutes is going to be 1 minus P. And the probability of seeing no car during all 20 minutes is going to be 1. Since every 5-minute interval is independent, then it's just 1 minus P to the power of 4, right? And this is going to be what? We know that at least 1 car on highway of any 20 minutes is this number. Then it's just 1 minus this 609 over 625. And this is 16 over 625. And you see, if you are enough familiar with numbers, you already know this 16 is, this 16 is 2 to the power of 4. And this is just what? This is just a 5 to the power of, let's see, 525. Yeah, 5 to the power of 4, right? And this is going to be 1 minus P is 4. So 1 minus P is 2 over 5. P is going to be 3 over 5. So there is a 3 over 5 chance that there is at least 1 car during any 5-minute interval. Okay, so basically that's all for the 10 questions of today. All these questions are quite classic and frequently asked during quant interviews. So thank you for watching. And we're going to see you next time. We're going to be talking about discrete and continuous distributions and all the statistics. Thank you.